Respected professors and colleagues, myself Nilina Bera, I am presenting my doctoral research work named Studies in Algorithm and Architectures for Sample Preparation with Digital Microfluidics. Now, what is digital microfluidics? It utilizes the technology of controlling the small amounts of fluids, that is transporting, mixing, merging, splitting, dispensing of droplets on a chip. Now here I am going to cover weighted mixed split of droplet, that is the WD algorithm, SIMOF, the optimal microfluidic sample dilution, it is a SIMOF algorithm, error optimization of the SIMOF sequences, and the analysis of volumetric split error for the DMRW algorithm. Now, what is basically 1 is to 1 mixed split steps? Now simply we have got a 3 by 1 set of electrodes. It is an array of electrodes, and we have got suppose two droplets of concentration factor C1 and C2, and where C1 not equal to C2. And we are following the electroweighting on dielectrode, that is EWOD technique, and there to following the actuation sequence, we are first mixing the droplet, and after that we are splitting the droplet. And while we are splitting the droplet, we are getting a different concentration factor. Now we are also in our research work I am following three different cases, that means three different mixing model. So first model is where k equal to l equal to 1, that means simply our 1 is to 1, that means balance mixing. Where k equal to l not equal to 1, that means still it is a balanced mixing, but it is 2 is to 2 or 3 is to 3 or 4 is to 4 or even 5 is to 5. We see it in the dilution and mixing with reduced wastage DMRW or improved dilution and mixing algorithm, that means IDMA. Now last one, it is our case 3, that is k not equal to 1 not equal to l, where obviously k and l are positive integer, but it can happen like 1 unit volume of one droplet, like one concentration is mixed with 2 unit volume of another concentration, that is 1 is to 2 mixing, or 2 is to 1 or 2 is to 3 in this way. Now it is basically weighted mixed split of droplet, that is WD. So we have studied the problem of generating dilution using a combination of 1 is to 1 and 1 is to 2 or 2 is to 1, that means a weighted mixed split operation. Okay, so over here we are basically considering splitting of 3 unit volume, that is 3x unit volume droplets into 3 unit volume, that is 1 unit volume 1x droplet. So this is basically the layout architecture. So we have got an array of electrode. So it is actually 5 into 5 array, and we have got time instances, four time instances. Now t equal to 0. So we have got one big droplet of size 3x, it's located. Okay, and this droplet is grounded. That is basically it is a low voltage. Like acha. After that, we are actually activating the electrode. That means we are creating three separate droplet, each of 1 unit volume. After that, we are trying to move the droplet to the right hand side. That means we are changing the actuation voltage. Okay, so to move a droplet, so we have to actually make the neighboring electrode activated. That means 1. So obviously it will be basically it is a pulling force. It will be pulling the droplet towards and move to the right hand side. Okay, Acha. Then obviously in the weighted dilution we have to generate obviously the fraction. Suppose we are basically taking suppose b. Okay, b number of balance step, and like w number of weighted steps. So obviously our denominator, we have pre-computed denominator, d is becoming 2 to the power b into 3 to the power w. So obviously total number of step is b plus w. So in this way, let's see. So we have got actually two sequences, mixing sequences. So first we have got one weighted steps, 2 is to 1, followed by a balance step. Another the last one, the third step is another weighted steps, 1 is to 2. Okay, and this way, so we are our denominator is obviously 2 to the power 1 into 3 to the power 2. So 2 is basically coming 1 is to 1 balance step. So it is coming 1 plus 1 2, and 3 is coming from weighted steps 2 plus 1 or like 1 plus 2, that means it's becoming 3. So that's why I am getting 2 to the power 1 into 3 to the power 2, that is the denominator is coming 18. So out of 18, so we are basically, the goal is to reach or the generate the fraction 5. Okay, 5 by 18. That means the target is to the concentration factor 5 by 18. So how to get that? So I am starting with the balance. I am calling with the weighted steps. I am calling 0 as my buffer and 18 as my sample. We are considering the numerator part. So with 2 is to 1, I am getting the numerator, the first C intermediate 6, and after that one balance step, I am getting the second C intermediate 3, and the final step, step 3, I am getting the target 5. So over here I am getting sample, just one drop of sample, 3 drops of buffer. The wastage is actually simple 1, and the output is 3. And the case 2, I have got another the mixing sequence, starting with the balanced 1 is to 1, then followed by 2 weighted steps 2 is to 1. And there also I am getting the numerator 5. It is coming, okay, and then the target is 5, and the same sample 1, buffer 3, waste is simply 1 waste, and the output is 3. Acha. Then how to generate, suppose 7 different fraction in a complete binary tree. Let's see. Over here the same, that's the 3 steps are there. So first step is balanced. B is for 1 is to 1. W1, it's a weighted steps, 2 is to 1. W2, another weighted steps, 1 is to 2. Now first starting with same, the buffer is 0, and the another sample is 18. So I am getting the first say intermediate 9. Now with 9 I am getting with a buffer and the intermediate 9, I am getting the 3. So I am following the weighted 2 is to 1 mixing. So I am getting the second C intermediate 3 in this particular branch, the left hand side. Right hand side branch, I am once again with 2 is to 1 mixing, I am getting the my second C intermediate 12 with 9, the first C intermediate, and the sample 18. Now the final, the leaf nodes, I am getting obviously with my buffer 0, and the third second C intermediate 3, I am getting 2, and I am following the mixed split operation with the weighted steps 1 is to 2. So I am getting altogether 7 different fractions. So over here I can create different sequences. Simply 1 is to 1, 1 is to 2, 1 is to 2, one entire branch is there. Another branch is suppose 1 is to 1, 2 is to 1, 2 is to 1. So in this way altogether I am getting 21 unique step sequences with the weighted dilution. Another example, same 3 steps are there, and the sequences are changing. So altogether I am getting 23 unique sequences. Now in this way, weighted dilution, I am comparing the result of the weighted dilution with the balanced dilution. Balance is basically 10 balance step with no weighted steps, and the weighted dilution I am getting 7 balance with 2 weighted steps. So altogether denominator is coming for the balanced dilution, purely balanced dilution, I am getting 1024 denominator, and for the weighted dilution I am getting 1152. So over here if I just check the waste count, that is my x-axis, and all the different target concentration factor in my y-axis, I am getting this bar diagram. I am getting this brown bars, those are for actually weighted dilution. Just for weight count 3 and 4, I am getting the maximum is coming. But for this balanced dilution, compared with the balanced dilution, it is getting for the balance, I am still getting these green bars, those are for representing the balanced one. It is the waste count is available for even for 6, 7, 8, the waste counts are there. But for the weighted dilution, waste counts are getting minimized. Okay, it is for 3, 4, 5, the count is there, but 6, 7, 8, 9, it is basically getting reduced. So weighted dilution is performing better than the balanced dilution. The same way for if I am comparing the step count based on my balance compared to the weight weighted dilution, I am getting the green bar, that is actually for the balanced one, pure balanced one. It is the step counts, it is getting me the maximum number of steps, basically over here the concentration factors above 500, it is getting the balance, the green bar is telling me the first step count 10, it is getting 500 concentration factor it is checking. But for the weighted, it is altogether within 400 concentration factor it is picking up all the different factors. So still obviously the weighted is performing better than the balanced one. The same way, input sample, the same thing for the weighted one, the the brown birds are getting diminished as we move further right direction from sample count 1 to 3 up to 9. So obviously the brown birds are getting minimized. Okay, now coming the CMOP algorithm. So how the CMOP is performing? So CMOP is actually simulation procedure for optimizing sample dilution. So CMOP actually takes a single input x, and that is x is actually the maximum number of balance. CMOP is purely balanced dilution method. And suppose for x the step count is I'm getting 4, x equal to 4. So obviously denominator for the CMOP the algorithm it is 2 to the power 4, that is 16. So CMOP tree I am going to explain with that. So this one is suppose for the 4 steps. So I am starting with the buffer 0 and the sample 2 to the power 4, that is 16. So first C intermediate I am getting 8. So the tree has got over here the second step I am getting actually 2 branches. So the very first step 1, so I am getting the first C intermediate 8. So actually I am getting buffer 0 is there, 8 is there, 16 is there. So step 2 I am getting 2 branches. One I am utilizing buffer with the C intermediate, and the other branch the right hand side I am utilizing the C intermediate 8 with the sample. So over here I am getting two more C intermediate 4 and 12. Now for the third step actually I am getting 3 branches. So over here whatever the new C intermediate I am creating, I am carrying forward all the initial buffer sample and also the like you know existing C intermediates. That means in my third step I am getting a lot. That means first buffer with the C newly created C intermediate 4, then in between another the over here, acha, another node I am getting 4, the newly created C intermediate with existing 8. Okay, and then the other one the last one over here, this particular node I am getting 4 and with the sample 16. So I am getting 2, 6 and 10, 3 new C intermediate. Same way the right hand side I am getting 6, 10 and 14. Now step 4 I am getting lot of C intermediate. That means 0, that is original buffer, then my sample, and in between the newly created 2, and then existing C intermediate 4 and 8. So I am getting 4 nodes over here. So I am getting altogether lot of leaf nodes. So that is my existing entire sim of tree, whatever it is possible I am getting all possible combination of my 1:1 balanced dilutions. Okay, and now I am going to compare with all the sim of sequences what is basically the optimal like you know optimal buffer sample usage, and the waste generation and also the steps. So over here in this particular sim of tree I am getting the fraction 5. Okay, 5 by 16 in 4 different ways. So what is basically the optimal sim of sequence? Let's try. Now 3 sim of sequences I am showing there. So 3 different way I am creating 5. Now let's see sim of sequence 1. So sample buffer waste. So the first one I am getting utilizing first 1 drop of sample, then 3 drops of buffer and 2 drops of waste. Then the second sim of sequence I am getting 2 drops of sample, 3 drops of buffer and waste individually. And then the third sim of sequence I am getting all sample buffer waste I am utilizing all 2 drops. That means if the end user wants to get the sim of sequence that optimizes the sample, so I need the sequence 1. If the end user wants the sim of sequence that optimizes waste, so I can get the sequence 1 or sequence 3. Okay, Acha, this is the way CMOP is actually working. Now CMOP I am actually trying with trying to compare with the existing sample dilution algorithms like IDMA, then TMRW, REMIA, GORMA, our existing WD, and obviously bit scanning. So altogether, CMOP over here, the waste droplet generation, CMOP is performing better than all six existing algorithm. Okay. Now, CMOP the symmetrical nature. Now I have suppose CMOP I am taking 10 steps. 10 steps mean total number of fraction. 10 steps the denominator is 2 to the power 10, that means 1024. So if it's a 1024, that means I can create all the fraction 1 to 1023, and then I can even cut it a two different set, 1 to 511, and then the complements are there in 513 to 1023. And here we have I have plotted over there, just check all the fraction within 1 to 511. It is performing in a the same, and basically the complementary fraction, they are performing in a symmetrical way. So one simple fraction 1, it has got the complement obviously 1023, and suppose fraction 511, it has got the complement 513. They are basically performing in a symmetrical nature. Sorry. Now, running time of the CMOP algorithm, just check input simply x equal to 3. So obviously 2 to the power 3, 8. So sample is 8. So total 9 cases are there. So time is negligible. Now, even if the input is suppose 9, that means the range, obviously the sample is 2 to the power 9, that means 512. Total CMOP cases, total number of different ways we can create the CMOP sequences. Altogether it is coming obviously 4 lakhs. Okay, so still the time is still it is really good. So simply 1 minute 8 second. Now even CMOP, suppose input x equal to 11, that means 2 to the power 11, okay, 2048. So it is the total cases is huge. But still the time is 2 hours, it is within control. And we ran our algorithm on an Intel Core i5, okay, 2.5 gigahertz processor, and just 8 GB of RAM. Still accuracy level for different inputs, it's still within the running time is basically market leading. Now the error propagation in the CMOP target. So obviously when suppose n equal to 5, so denominator to the power 5, that means 32. So it is basically the target, suppose it is 9, so 9 by 32. So there is actually how it is performing. So this is basically 5 steps. So there error, suppose error is coming we are assuming that there is a volumetric error if there is a waste. Okay, and then when I am splitting droplet, splitting suppose 2x volume of droplet, and if there is a problem, if there is the electrode is positively polarized, so maybe while splitting it will split an additional droplet. So obviously it will become when this error, some extra additional volume is getting split, that means error is suppose epsilon. So 1 plus epsilon, this epsilon is basically error in the volume, we call it as a volumetric error. So if there is obviously you have to balance it. So if there is 1 plus epsilon, so it should be waste should be 1 minus epsilon. So altogether it will be coming becoming the same way 2. Okay, then obviously this 1 plus epsilon, it is basically propagated along. So obviously the concentration factor, it will be becoming it will be changed. So over there, so the volume will become obviously 2 plus epsilon plus 2. So from C4 we have take the concentration factor different, it is changing it. So C4 prime and C5 prime. So what is this C5 is becoming, instead of getting it obviously 9, we are getting the altered concentration factor at the final step 8.93, 827. Okay, so now the concentration factor is changed. So obviously, so the deviation, so 9 minus this 8.938. So deviation is coming. The result value I am getting 0.06. So this one, there is a threshold. So if the deviation is actually obviously absolute value of the deviation, if it is less than plus zero point 0.5, so it is actually, we call it non-critical. So it is acceptable, it is optimized. Okay, but if it is greater than 0.5, that means it is error is there, and we have to minimize the error, or we have to remove or nullify the error. Okay, so there is a concept of critical and non-critical error. Now we have compared the performance of BS, bit scanning, and the SIM of targets with 7% volume error. That means this epsilon is actually your 7%. That means 0.07, 5%, 0.05, 10%, 0.1. Okay, this is basically the all different extra additional volume error we have basically tried to check with the volume error how the targets are performing. Okay, now we are going to reach, so here x equal to total number of steps equal to 1024, and our target we have to want to reach the numerator 341, and the deviation we have to checking the deviation threshold is still we have to check whether it is less than or greater than zero point 0.5. So this is basically the plot. Just check the CMOP it is basically within the limit. It is like if 341 is the target, so obviously the range is 341 plus 5 or 345 plus 5. So CMOB is basically the yellow dots. It is basically the final CF. The altered final CF is 341.048. Within range, so it is non-critical. But compared with CMOB, bit scanning is really way above the range. So bit scanning, the final CF is becoming 357.238. So that is really, it is a problematic. Okay. Now, this is basically the analysis of volumetric split error for the DMRW algorithm. So after CMOP, we are getting the same thing. We are trying to find out how the performance of error in the achieving a target concentration factor in the existing market leading algorithm DMRW, dilution and mixing with reduced wastage. So let's see. So this is basically a well-known target 313 upon 1024. So 10 steps are there, and this is the way we are basically creating the DMRW diagram. And here we need the 3 volumes of 3 drops of sample, 6 drops of buffer, and we are generated 7 waste droplets. Okay, so let's see how to how it is performing when we introduce error in different steps. Now this is basically fully exploded diagram. Suppose we are generate getting the waste the very first step. Okay, first step matlab like this one, 512 by 1024, that is the very first step. Now there basically the waste is there, and there basically it is basically kind of progressing. Okay, acha, this is a fully exploded diagram. Now suppose this one very first acha, 1:1, so it basically 3 into 1 array of electrode. So we have got basically we need 3 drops of, just check over here, 3 drops of buffer with 3 drops of sample, just to create 6 drops of 512. After that, the 6 drop of 512, 2 drops of 512 is getting propagated to the higher step to generate the second C intermediate 256, and then another 2 drops we are getting the third C intermediate 384. So basically when you are creating 6 drops, so 5 drops we are utilizing, so we are getting 1 waste. So this is the way we are basically fully exploded diagram. We have created how many what is basically the ways different 7 different ways to create 7 waste droplets. Okay, now here we have there is a, we have got observed the performance of DMRW. We observe that if we introduce volume error on the higher side of the diagram, higher side matlab this one, this is the higher side, the right hand side, and the left hand side is the lower side. So becoming the higher side becomes more critical when the error is introduced early. Just check over here, the target is 61 upon 10 steps 1024, and I am introducing 10% of volume error, and over here, so it is becoming critical the very first step. It is it is instead of 61, so final altered final CF, it is giving me 66.31, and obviously minus 10%, just a negative error, same, it is basically giving me a symmetrical nature of the performance of the volume error. Now, same way, the effect of positive and negative volume error is the same, like positive, plus 5, minus 5, and then plus minus 7%, plus minus 10%. It is also kind of giving me a mirror effect. Now, deviation also becoming symmetrical. So one target suppose 6 corresponding obviously The 6, it is like corresponding 1018, it is the complement. And basically each and every complement there, basically deviation is also symmetrical. Now 121, it is corresponding the complement is 903. Same way 496, corresponding it is the complement is 528. Just like the deviations are also symmetrical. Now, obviously, the conclusion, the future direction, we plan to introduce a simulation guided optimization procedure using a combination of balanced and the weighted dilution to achieve the multiple target concentration, that is the future goal, so MTCWD. And the compared to the existing balanced dilution algorithm, the MTCWD scheme aim to prepare certain dilution of a fluid sample simultaneously when optimizing mixed split, generated waste droplet, input sample, and buffer droplet. And the future research on the MTCWD will show that if the technology permits, introducing the weighted steps, one is to two steps along with the balance step, actually reduces the effect of unbalanced mixed split errors in the final concentration factors. So those are basically the publications of international conference. I have got two journals and I have got patent with my supervisors, Professor Dr. Shubhashish Majumdar and Professor Dr. Bhargav Bhattacharya. Thank you all.